Hey everyone, and welcome. Today, we're going to tackle a true rite of passage for anyone who's into IT or tech, making your very own Ethernet cable. Seriously, if you're studying for your CCNA or you just want to level up your home networking game, this is a skill you absolutely want to have. All right, let's get right into it.
Okay, but let's be real. That brings up the big question, right? You can just go to the store and buy one. And for most people, most of the time, that's exactly what you should do. So why on earth would you ever need to make one from scratch? Well, it turns out there are some really good, totally legitimate reasons. Maybe you're running cable through the walls of your house or office and you need that perfect custom length for a super clean install. Or, and this happens all the time, that little plastic clip on an existing cable snaps off and you just need to repair it. For big custom jobs, making your own is almost always cheaper. And honestly, it's just a core networking skill that's super valuable to have in your back pocket. So here's how we're going to break this down. Think of it like a how-to sandwich. We'll start with the practical stuff, the tools, and the first few steps. Then we're going to pause and take a deep dive into the why, the anatomy of the cable and how it actually sends data, which is the really fascinating part. After that, we'll jump right back to finish up and test the cable you're building. All right, let's kick things off with section 1, why make your own cable? And we'll start with getting the right tools for the job. Okay, so here's your toolkit. First up, you need some bulk Ethernet cable. We're using Cat5e UTP, which is pretty much the standard for most situations. You'll also need a handful of RJ45 connector heads, a crimping tool to attach them, and while this is technically optional, a cable tester is going to save you so many headaches, trust me. And of course, the two most important tools, coffee and patience. Those are not optional. Okay, time to get our hands dirty. First, make a nice, clean cut on the end of your cable. Now take a look at your crimper. It should have a slot with a little blade in it. You're going to slide about an inch of the cable in there. Now don't go crazy here, you're not trying to cut through it. Just a gentle squeeze is all it takes to score or kind of scratch that outer jacket. The key is to not nick the tiny little wires inside. Once it's scored, just bend it back and forth a couple of times and the jacket will break clean, letting you pull it right off. And when you pull that off, you're looking at 4 pairs of colorful wires, all twisted together. And this is where we take a little detour. We're going to pivot from the how to the why. I mean, these little wires are literally how you're watching this explainer right now. But what's the deal with the twists? Why aren't they just straight? And that's the perfect lead-in to section 2, the anatomy of a network cable. This is where we uncover the hidden and kind of brilliant genius behind those simple twisted wires. You see, the data zipping through these wires has enemies. The first one is called EMI, or electromagnetic interference. This is basically electrical noise from things like power cords, fluorescent lights, motors, anything that can mess with the signal. The second enemy is crosstalk, and that's when the signal from one wire inside the cable actually interferes with a neighboring wire. And the simple, elegant, absolutely brilliant solution to both of these problems? Just twisting the pairs of wires together. It creates a canceling effect that neutralizes all that unwanted noise. So the cable we're making today, it relies only on those twists for protection. That's why it's called UTP, or unshielded twisted pair. It's what you'll find in pretty much every home and office. There is a tougher version called STP, or shielded twisted pair, which adds an extra layer of foil shielding for protection. You'd only really need that in places with a ton of EMI, like a factory floor. For our purposes, UTP is perfect. And it's kind of wild when you think about how fast this tech has evolved. Back in 1990, we were thrilled to get 10 megabits per second with Cat3 wires. Just 5 years later, Cat5 took us to 100 megabits. And by 1999, the Cat5e wires we're still using today got us to a full gigabit per second. Here's a key thing to remember. That Cat number, Cat5e, Cat6, it's referring to the quality of the individual copper wires inside, not the cable as a whole. Okay, so now we know why the cable is built this way. But how does it actually work? Let's dive into section 3, how wires send data. This is where the real magic happens. Think of it like this. It's all about translation. Computers, at their core, speak in binary. They think in ones and zeros. But copper wires? They don't get binary. They speak the language of electricity. They speak in voltage. So how do you make that translation happen? Well, and this is a super simplified way to look at it, but the basic idea is that a network device, like your computer, will send a positive voltage, maybe positive 2.5 volts, down the wire to represent a 1. And to send a 0, it'll send a negative voltage, like negative 2.5 volts. By flipping between these positive and negative voltages incredibly fast, it can send a massive stream of ones and zeros. It's just mind-blowing when you think about it. Now, for this to work, the devices on each end have to agree on which wires are for talking and which are for listening. For example, a computer typically transmits or talks on pins 1 and 2, and it receives or listens on pins 3 and 6. A network switch does the exact opposite. So if you're connecting a PC to a switch, you use a straight-through cable, where pin 1 connects to pin 1, 2 to 2, and so on. But back in the day, if you wanted to connect two computers directly, you needed a special crossover cable that would connect the talk pins on one side to the listen pins on the other. But, and this is the really cool part, you probably don't have to worry about this anymore. Almost all modern network gear has this magical feature called Auto MDIX. These devices are smart enough to automatically detect what they're plugged into and just switch their own internal wiring to make it work. It's a total lifesaver, and it's the reason crossover cables have pretty much gone extinct. Okay, there's one really important rule you gotta remember with this amazing tech: distance. A standard copper Ethernet cable has a maximum length of 100 meters, which is about 328 feet. If you try to go longer than that, the electrical signal just starts to get weak and fall apart. You'll get errors, something called late collisions, and basically, your connection is gonna be awful. All right, theory time is over. Let's get back to actually building our cable. Welcome to section 4, arranging the wires. And I'm not kidding. This next part is the most critical step of the whole process. If you get this wrong, the cable just won't work, period. So, we're making what's called a straight-through cable, and for that, we use the 568B wiring standard. You're going to want to memorize this. You'll untwist the pairs, straighten them all out, and line them up from left to right in this exact order. White-orange, then orange. White-green, then blue. White-blue, then green. And finally, white-brown and brown. Get them all nice and flat, like a little ribbon. Okay, once you've got them in that perfect order, pinch them tight and use your crimper to make one clean, straight cut across the top, leaving about ½ inch of wire sticking out. Now, grab one of your RJ45 connectors. This is super important. Hold it so the little plastic clip is facing down, away from you. Now, just gently slide that ribbon of wires all the way into the connector until they hit the very end. You also want to make sure the blue outer jacket gets pushed a little bit inside the connector for support. Then, slide the whole assembly into your crimper and give it one firm, confident squeeze. You'll hear a little click. Awesome. Now you just do that exact same thing on the other end of the cable, using the same 568B color order. Which brings us to our final section, finishing and testing your cable. This is the moment of truth. Did it actually work? And this is where that little cable tester becomes your best friend. You plug one end into the main unit and the other into the remote part. When you turn it on, it sends a little pulse down each of the 8 wires. On a perfectly wired cable, you'll see the lights blink in perfect sequence on both sides. 1 and 1 light up, then 2 and 2, 3 and 3, all the way to 8. If the lights blink out of order or if one doesn't light up at all, you know you messed something up. No big deal, just cut the end off and try again. So let's just quickly recap the big ideas here. First, twisting the wires is a beautifully simple but absolutely genius way to fight off electrical interference. Second, the wire order is everything. That 568B standard is the key to making a standard straight-through cable. And finally, while old-school Ethernet had specific wires for talking and listening, modern tech like Gigabit Ethernet and Auto MDIX is so smart it can send and receive data on all the pairs at the same time. It's just incredible. You know, when you really stop and think about it, it's just incredible. This little cable that you can make with your own 2 hands is a true marvel of engineering, built on decades of innovation. It's the thing that literally connects us all to the world. So now that you know how to build one, what are you going to build with it?